So the second video on Lagrange multipliers is actually 13.1. This is what happens when I'm rushing. Anyway, welcome to Calculus 3, and I lost the track of everything else. We are moving to chapter 13. We are talking about multiple integration and over rectangular region. First off, what can we use double integrals for? We can use them to find either area or volume of objects. So to remember a little bit from before in Calc 1 with K's, we know that we can find area if we take the integral of a function. Now, there is one dimension coming from f of x, which is the height, and then the length is the width is delta x, which is between a and b. So length times width is the area. There is a multiplication in between and dx. So dx is for decoration. It's actually width of our area. So now, how did that work? If you have, let's say, function y equals 3, and you want to compute the area between 2 and 6. You can 4 units this way, 3 units this way, and area is 4 times 3. But then you're a kid tutoring or someone, and they ask their famous why, right? That's when you set up the integral to explain why. So how does the integration works? The area is integral 2 to 6 of your function f of x, which is the integral is 3x from 2 to 6, which is 3 times 6 is 18 minus 6, which is 12. That's why. Now, important thing to understand as you are setting up these integrals from Calc 1, which will be extremely important for Calc 3 for chapter 13, is this idea of representative rectangle dx, which will appear in about 15-20 minutes because of the lag. Now, this representative rectangle, there it is, dx, is the one that swipes between 2 and 6, and that's the limit. So dx swipes from left to right, the way we read, and it will take on all of the x values between 2 and 6. So integral sign with 2 and 6 and dx, which is the rectangle, are together length. And then the height is given by a function. So function times dx equals area. Now we're moving into the realm of Calc 3, and we are talking about double integrals. I will start with the concept that the double integral can represent area, eventually showing up, or could represent volume if written in this form, which will eventually show up. Now, why is this area and why is this volume? Remember your dimension. Here is one length, here is another length, length in x direction, length in y direction, length times height, area. Here is one dimension, here is the second, here is the third, 3D. This is something you really have to understand in order to set up the integrals in this chapter and before going on here? So if you are not integrating a function here, then it's a 2D because you only have 2 dimensions. If there is a function there, 1, 2, 3, 3D, it's a volume. So now how do I solve the problem from up there using Calc 3? Well, we have exactly the same setup. We have our x, we have our y, we have our there, and then from 2 to 6. I am going to set up the double integral, and I know I need to go dx and dy, and we are going to take a look at delta x first. Delta x is going to swipe 2 to 6. So the limits on the inner integral are 2 to 6 because that inner integral corresponds to dx. Think of the layers of the onion. There is a layer inside, then there are a layer around, and the layer around, and around, and around, and around. You can chain as many integrals as you want. We will only be working with the double and triple integrals in this class, but you could have 17 integrals chained together. The important thing is that the inner integral corresponds to the inner dx in this case, and then the outer integral corresponds to the outer, in this case, dy. So now if I draw dy, it would be like this, and you see that the dy, well, you will eventually see that the dy swipes from bottom up, and the dy goes from 0 to 3. So the limits of integration for the red rectangle are left and right because d from left to right, so dx, which is the inner integral, is all of the x values between horizontal one, hopefully you remember your calc, from 0 all the way to 0 to 3 for dy. About assigning values for your appropriate variable. The inner integral, the red one, that's dx, so x values go with the x integral, y values go with the y integral. To solve this, I will put this box like this. Actually, no, I can copy it. Let me copy it one more time. There we go. And now I'm going to box off the inner integral. So you will work out the inner integral. And that would be, in this case, just x computed from 2 to 6. And you still have the dy outer integral to work with. You all know this. You did your quizzes already. Right? You learned it on your own. Or you use Mathematica and you still have no clue what's going on. So now we compute the inner integral. So that's 6 minus 2. We still have dy, which is integral 0 to 3 of 4 dy, which is 4y computed from 0 to 12 again. So now, if you about and wonders about the area, you can actually also do the double integral. Now, also, same problem. Could be done by using dy dx instead of dx dy. The limits would swap because now you have dy dx like this. X limits are 2 and 6 on the outside, 0 to 3 on the inside. Insert work here equals 12 on the other end. And now I'm going to write this in blood. You are allowed to switch order of integration only if you have rectangular region. Now this statement won't make much sense until tomorrow, because tomorrow we'll do 13.2, which is general regions. But this statement doesn't have a lot of sense. You saw me switch an example earlier. We still got 12. And we'll see that in the next section, switching these is going to make a lot more noise. So that's now. Here's the object, which has z equals blah. All right. Is this object over a rectangular region? And the answer is hell no, because not a rectangle, right? Good. Printer is next. If you look at the top of this printer, this is not just a flat, it's not just a box, right? Because of the irregular top, this printer has some kind of z function to it. Z equals blah. Is this particular surface done? Yes, it is. All right? So what is a rectangle in the domain? You have rectangular region. If it's not, it's a general region. So this one over here falls in a category of general region shapes. And we would have to integrate this one in actually polar coordinates. No, cylindrical coordinates for this one. Coming up, 13.4. So that's there. So now, you are allowed to change the order of integration by simply swapping dx dy, and if you have rectangular region. That's this. For general region, hell no. And well, now, if you have some kind of a rectangular region in your domain, you have some kind of an object on top, you can find the volume of this type of an object, right? Because the walls of the object will be the same like printer. It's going straight down. It's like taking a rectangular cookie cutter and making where the top of the function could be whatever, that's governed by our function that you get to plug in. But the shape on the bottom angle, and you can find the x goes from point A to point B, and y goes from point C to point D. So, rectangular region integral be volume equals A to B to D f of xy dy dx, or volume is C to D A to B f of y dx dy. You get to set this up looking at the shape. We can swap them only ones that are going to have functions in limits, and because they're going to have functions as limits to be in the first integral on the outer integral, because then you would not get the number at the end to be volume equals 7 or something. All right, guys, so when you are integrating, you will have the integral in terms of x, integrals in terms of y. You always keep other, so if you're integrating in terms of x, y is the constant, and you treat it as constant, you just copy it. If you integrate in terms of y, x is a constant. So now that you know that, integrate this, again, inner integral first and then the outer integral. X dy dx 1 to 3, 0 to pi over 2. All right, so are we integrating in respect of x or y first? Very good. So the inner integral is dy. So we keep, oops, so we keep x as a constant. Copy integral 1 to 3. And now integral, what's the integral of sine y? Negative cosine. So I have negative x cosine y computed from 0 to pi over 2, and I still have dx because that's for the. So now we're computing the inside. So from 1 to 3, I have negative x open parenthesis cosine of pi over 2 minus cosine of 0. I still have dx. Now, cosine of pi over 2 is? Very good. And the cosine of 0 is? So I have 0 times 0 minus 1, that's negative 1, and the negative in front. This reduces down to x dx, which is x squared over 2 from 1 to 3, which is 9 halves minus 1 half, 8 halves, which is 4. Do we all agree? Yes, we do. Perfect. Now, some problems are set up in a different way. So here is, no, that's, Here's problem 21. Now this is how it's posed. Find the integral over the rectangular region of the square y dA, where the region is given by all x and y such that 0 less than x less than 1, x less than equal than 1, and y less than 4, less equal than y less equal than 4. This is how the this is how the problem looks like. Notation over here. This R over here is telling you that you are over a rectangular region, and that R is explained here, that the limits for x are 0 and 1, and limits for y are 1 and 4. It's very simple. dA over here gives you an option to either do dx dy or dy dx. You see? So when you have this, you have the freedom